So that's the basics of modular arithmetic, and particularly an emphasis on why working modulo primes is so nice. We'll talk again more about working modulo composite numbers later, but I wanted to talk a little bit about applications of modular arithmetic, both on the theoretical side and the computational side. Now, first off, I should note that nearly every cryptosystem relies on modular arithmetic in some fashion. And this is why we've already started to highlight what the algorithms look like to do some things in modular arithmetic. For example, calculating inverses is something we're going to need to be able to do, and we're going to need to know how to do it efficiently. Next week, we're going to talk about a lot more algorithms that are going to allow us to do other things in modular arithmetic, so that we can start nailing down what things are easy and what things are capital H hard. The second thing we talked about that modular arithmetic often gets used for is for what I'm going to call the reduction maps, by which I mean that the mod n world comes completely from the integer world. And so, really, each mod n world is reflecting the structures of the integers themselves. And so there are a lot of questions that you can ask about the integers that you can actually answer by using modular arithmetic for the right modulus. So I'm going to show you a couple examples. I did some examples in lecture. There's some examples on the homework. I'll show you a couple of other examples here of the sorts of questions that you can answer by using these things that I'm going to call reduction maps. And so most of the things where I'm going to apply this are going to be what are called Diophantine equations. And Diophantine equations are a lot of what number theorists have thought about historically. Namely, what's a Diophantine equation? It's a polynomial equation with more than one variable where you're looking for solutions in integers only. So for example, you could take the equation x squared plus y squared equals z squared, and you would discover solutions like 3, 4, 5, or 5, 12, 13. Probably it won't take you very long to realize what I'm writing down here are Pythagorean triples. And so actually there's some connection between this equation and the Pythagorean theorem. But we certainly know there's at least these solutions. And in fact, there are tons of integral solutions to this equation. In fact, I promise later we'll actually write down all the solutions to this equation. But there are tons of them. Let me make a slight tweak to this. Structurally, this equation looks very similar to this equation. If you graphed this in R3, it would be some sort of hyperboloid, and indeed the graph of this would look exactly the same. It would also be a hyperboloid. If we were talking about calculus 3 stuff or multivariable functions or physics or whatever, these two equations would behave in every way identically. But because we're talking about integers, there's this whole weird thing that happens where the equations end up being incredibly sensitive, and the slightest tweak to your equation can change the behavior radically. So in fact, actually, whereas this equation had infinitely many solutions, of which these are but 2, this equation has only one solution. And that one solution is x, y, and z all 0. Now, this sensitivity is something that some people will absolutely love about number theory. So I think this is awesome, and I think the fact that there's tons of examples where you change the equation just slightly and suddenly there's no solution, or there's tons of solutions, or it just behaves in some random way. I think that's really neat and interesting and reflects some really deep structure of the integers and all of that kind of thing. So I'm a big fan. Other people get driven away from number theory because they find this absolutely maddening. And there are a lot of worse examples that we'll talk about later where we'll explain how sort of like very similar looking equations end up having surprisingly different behaviors, and it's often quite difficult to explain why they behave differently. In this case, I want to prove to you that in fact this equation has only one solution. And how am I going to prove to you that this equation has only one solution? I am going to look at what the solutions of this equation are, mod 3. Now, I could look at what the solutions of this equation are, mod anything. I could look at it mod 17 if I wanted. The reason why mod 3 is appealing is that that will make this whole term just disappear. So again, the key insight into thinking about this is every integer solution to this equation will yield a solution mod 3. So what I'm going to do is I'm going to start by supposing I have a solution, and then I'm going to look at it mod 3 and think about what could it be. Now, the question about what the solutions to this are mod 3 is much more tractable. And by tractable, I mean it's actually quite easy, because there's only 3 things x, y, and z can be, and what z is doesn't even matter, so really there's only 3 things x can be and 3 things y can be. And so there are 9 total things to check. And so at absolute worst, what you can do is you can make a table of all the possible x's and all the possible y's, and then see what the solutions to this equation are mod 3. But actually, it works out to be even easier than that. And the reason why is because of what the squares are mod 3. So I'm going to pick some neutral letter. I'm going to pick a, and I'm going to write down what a squared mod 3 is. So 0 squared is 0, 1 squared is 1, and 2 squared is 4, which is 1. So the only squares, mod 3, are 0 and 1. So, when I look at this equation mod 3, what happens? Well, 3z squared is just 0 mod 3. X squared is a square, so it is 0 or 1. Y squared is a square, so it is 0 or 1. So mod 3, whatever x, y, and z are, 3z squared is 0, y squared is 0 or 1, and x squared is 0 or 1. So here's what I have to observe. Mod 3, there's only one solution for x and y. Namely, I need x squared to be 0, and I need y squared to be 0. Why? Well, what are the other possibilities? Well, 1 is 0 and 1 is 1. Well, then I get 0 plus 1, which is 1 mod 3. That's not 0. Or they're both 1, in which case I get 1 plus 1, which is 2 mod 3, but 2's not 0 mod 3. And so the only way this works is if x squared and y squared are 0 mod 3. But a quick look at my table tells me the only way for x squared and y squared to be 0 mod 3 is for x and y to both be 0 mod 3. And so what I've done here is I've managed to use this mod 3 information to deduce information about the integer solutions. Namely, the integers that solve this must both be 0 mod 3, which in fact means they're both divisible by 3. And so what I'm going to do is I'm going to rewrite x and y as multiples of 3. And so I'll go ahead and write x is 3k and y is 3l. And let's substitute that back into our original equation. And remember, I don't know anything about z, because z actually just disappeared completely from the equation when I looked at it mod 3. So currently, as far as z goes, I have absolutely no idea what's going on. Z could be anything, so I'm just leaving z here. Okay, so once I simplify this out, that will give me 9k squared plus 9l squared equals 3z squared. I now notice that I can divide through by 3, so I'll do that. In fact, I'm going to factor a 3 out of the left, too. So I divided through by 3, which gave me 3k squared plus 3l squared, and then factored the 3 out. Again, I'm trying to show there's only one solution here. So in my mind, if you believe what I'm trying to show here, I actually know that x, y, and z are all 0. That's the only possibility, because that's what I'm trying to prove. But currently, all I'm working with is the assumption that x, y, and z are integers that satisfy this original equation, x squared plus y squared equals 3z squared. Now, in fact, this is the key equation here. Because this now tells me that 3 divides z squared. But the only way for 3 to divide z squared is for 3 to divide z. Again, this is a consequence of unique factorization. Really, this is the p divides ab implies p divides a or p divides b thing that we talked about for primes, because z squared is just z times z. And so if 3 divides z times z, 3 divides z, or 3 divides z. So 3 divides z. So just like I was able to rewrite x and y in terms of k and l, Z is also a multiple of 3, so I can also rewrite Z. And so I'll go ahead and rewrite Z as 3m. And then I'll plug that into my equation, so I get 3 times k squared plus L squared equals 3m squared. So 9m squared. And about this point, you're probably wondering where on earth this could possibly be going, because it's like, yeah, I'm plugging things in places and stuff is canceling and all sorts of good stuff. But this seems really weird. But all you really have to do is sort of follow your nose through the algebra here. What do I know? Well, these things have to be 0 mod 3, so I'll plug that in. What does that tell me? Okay, well, now I can do this. Oh, well, now there's a 3 factor over on this side, so there has to be a 3 factor over on this side. Plug that in. So we get here. And so k squared plus L squared is 3m squared. Now, partially you might be thinking, doesn't it feel an awful lot like we're running around in circles here? And if you were thinking that before, you probably definitely think that now, because what I've done is an awful lot of work. And where am I now? I am exactly where I started, after a page and a half of work. Namely, I now have k squared plus L squared equals 3m squared, which, hey, is just x squared plus y squared equals 3z squared with different letters. And that sure seems an awful lot like it's not going to be useful. Because if I knew how to solve this equation, well, I definitely know how to solve this equation. But here is where Fermat noticed something very useful. What we just proved is that KLM is also a solution to our original equation in integers. Let me frame this in a more suggestive way. So if I start with any integer solution here, then I get another integer solution, namely x over 3, y over 3, z over 3. Emphasis here, this is still an integer solution, because remember, we got here by showing that x and y and z were all divisible by 3. So x over 3, y over 3, and z over 3 are all integers. Namely, k is x over 3, L is y over 3, and m is z over 3. Now, this might raise your spider senses a bit, because I started with an integer, and then I divided it by some stuff, and I claim it's still an integer. And I mean, a priori, that's not a problem, right? This could be like 9, 9, and 18. And so I divide it by 3, by 3, and by 3, and I would get 3, 3, and 6. That's still integers, that's fine. But the thing is, I can apply this same statement to this integer solution. And so again, if I started with 9, 9, 18, which is not really a solution to the equation, but imagine it was, this magic formula that we just did would tell me, okay, well, so is 3, 3, 6. Well, that's an integer solution. So is 1, 1, 2. No problem yet. But now when I say, okay, this is an integer solution, so is 1/3, 1/3, 2/3, now math is broke. So here's the key point. When I use this method to go from a solution to another solution, I'm actually producing a smaller solution, unless my original solution was 0, 0, 0. If any of x or y or z is not 0, then the solution I've produced here is smaller. I've pulled one of the 3's out of x, y, and z. And you can only do that a finite number of times, right? Perhaps 3 to the 18th divides x. But then I can do this 19 times, and then I will divide it, and I'll be claiming something's an integer that's not really an integer. And so, in fact, the only integer that is infinitely divisible by 3 is 0. And so that, in a very roundabout way, proves to me that, in fact, the only possible solution to this equation is 0, 0, 0. This proof method, I'll go ahead and note, is due to Fermat. And Fermat called this proof method infinite descent. And the mental image you're supposed to have with the phrase infinite descent is that the solutions are getting smaller and smaller and smaller and smaller. And the thing is, integers can't get smaller forever. if I start with an integer, it can only get smaller finitely many times in absolute value. So if I start with an integer like 20, it can only get strictly smaller at most 20 times. This is a very different thing than the real numbers. I can certainly have real numbers that get arbitrarily close to 0. So for example, I could start with 1, a third, a ninth, a 27th. I can divide real numbers by 3 all day long. But I cannot keep making strictly smaller integer solutions to something. Eventually, I run out. One thing that modular arithmetic lets you do is it gives you a really powerful tool for studying equations of the integers themselves. So even though this was a question about the integers that did not mention mod 3 at all, looking at this mod 3 revealed the structure that was hidden inside this equation and allowed us to determine what the solutions to this equation were. Now, a question you might ask is, okay, great. So can I answer all the questions that I want about Diophantine equations by looking mod numbers? Like, for example, could I prove that I have the complete set of solutions to a Diophantine equation, or prove that there aren't any solutions, or find if there are solutions? These kinds of questions. And unfortunately, as much as number theorists wish the answer to that question was yes, it turns out that the answer is no. That there are lots of Diophantine equations that have lots of solutions mod every n you could possibly look, but then actually have no integer solutions. And indeed, this is an area of fairly active study. Now, I called this map from z to the integers mod n a reduction map. I want to point out, though, that there's not only reduction maps from the integers to mod n. There are reduction maps between some moduli. So, if d is a divisor of n, then we can reduce mod n equations to mod d equations. Note, this hypothesis here is really important. So in particular, if you have a mod 12 equation, you cannot reduce it mod 10, because 10 does not divide 12. The reason why this works when d divides n is that the mod d buckets are all unions of mod n buckets. So if n is 6, well, there's 6 buckets, mod 6. And then I look, say, mod 3. Mod 3, there are 3 buckets. But if you think about it, you can convince yourself the 3L bucket is exactly the 6K bucket and the 6K plus 3 bucket. The 3L plus 1 bucket is exactly the 6K plus 1 bucket and the 6K plus 4 bucket. And the 3L plus 2 bucket is exactly the 6K plus 2 bucket and the 6K plus 5 bucket. So these 6 buckets become 3 buckets, and you just dump the entire contents of 2 of them into here. So anything that was true about these buckets up here still gives you something that's true about these buckets down here. If you attempted to make a similar construction, but for mod 12 into mod 10, it will not work, because if I know what a number is mod 12, that doesn't tell me what the number is mod 10. So we can play almost exactly the same game that we played in the previous example with modular equations. So I could look at this equation, mod 1024, famously a power of 2, and I could ask, does this equation have a solution? Now, technically, there's only a million-ish possibilities, because there's 1024 possibilities for x, 1024 possibilities for y, and so I could just plug them all in and figure out whether the answer is yes or no. You could also try and guess. Good luck. But what you might notice is that, in fact, I can reduce this equation mod 1024 further. So I could try reducing it, for example, mod, well, what would be the easiest thing? 2. If I reduce this mod 2, I would get to x squared plus y squared plus 1 is 0 mod 2. Unfortunately, this has solutions. So 1, 0 is a solution. I should note, by the way, when I'm doing this trick, This trick is only really going to work if the answer is there's not any solutions. If there are solutions, the best I can hope for is that I'm going to be able to figure out what the solutions are by sort of putting together the pieces from these things. But I'm really hoping when I look at this that there's not a solution, which disappointingly was not the case here. So this did not really tell me anything. But perhaps I was a bit too greedy. Maybe instead of looking mod 2, let's look mod 4, because 4 is also a divisor of 1024. And so let's look at x squared plus y squared plus 1 equal to 0 mod 4. And I'll go ahead and tell you this has no solutions. Why does this have no solutions? Well, let's look at our same thing we did in the last problem. Let's look at the squares mod 4. 0 squared is 0, 1 squared is 1, 2 squared is 0, and 3 squared, 3 times 3 is 9, that's 1. And so 0 and 1 are the only squares mod 4. So if we mark up this equation, this x squared is 0 or 1. This y squared is 0 or 1. And so what I'm trying to do is 0 or 1 plus 0 or 1 plus 1 equals 0, mod 4. And there's only 4 possibilities here, and none of them work. 0, 0, no. 0, 1, no. 1, 1, no. So this has no solutions. But the fact that this equation has no solutions means there can't have been any solutions mod 1024. Because if there were, I could reduce them mod 4 and I'd get a solution. So the answer here ends up being no. You actually can't get any solutions to this mod 1024. And so even though ostensibly this is a much more difficult question, I'm able to answer it by answering this much simpler question, which is really a lot of what we hope to be able to do on the theoretical side with modular arithmetic. The last note here is really a preview of what we're going to be talking about later, which is called the Chinese remainder theorem. And what this roughly says is if you understand the reduction maps of mod n to each prime power dividing n, that's enough to completely understand everything mod n. So, said somewhat informally, what the Chinese remainder theorem is ultimately going to tell us is that if I think about what the mod n world looks like, it's really just a combination of the mod p to the k worlds for the prime powers that divide n. And so ultimately, when we go to talk about RSA, which is going to be one of our big cryptosystems we talk about, what it's going to be based on is the idea that you're going to pick a number n, and it's going to be a product of 2 primes. You're going to make that n public, but you're going to keep the primes secret. And so what that means is, you know the primes, but no one else does. So when you do operations mod n, what you can actually do is reduce them to mod p and mod q. That is, you can use the 2 reduction maps to work mod primes. And remember, one of our biggest themes from this whole section has been working mod primes is way better than working mod anything else. But because these primes are secret, no one else can work mod the primes. They're stuck working modulo n. So they're stuck doing all of their calculations mod a composite number, which remember was the ugliest possible option. And so why is it that you're able ultimately to decrypt messages and everyone else isn't? It's because of the additional leverage you get by the fact that you get to work mod primes and no one else does. So ultimately, how much nicer is working mod a prime than working mod a composite? It's enough nicer that the additional computational power you get by being able to work modulo primes is enough to protect your information from those who are forced to work modulo composite numbers. Okay, I'll wrap up the chapter review here. We'll pick up next week where we'll be talking about algorithmic efficiency, and we'll be talking about big O notation and how we're going to measure how efficient an algorithm is. And then, of course, we'll start talking about some algorithms for working with modular arithmetic and how efficient they are. But until next time, be well.